Hello, everybody. Welcome to lecture 11, where the main topic is actually this one, the chain rule. But we're also going to have one slide about higher order derivatives. Let's get right into that. There isn't much to say about this other than for many useful reasons that we're going to see later. Sometimes you may actually want to differentiate. This means take a derivative of a function more than once. So for us, it's going to be twice when we do applications of this stuff. So here are just some notations that you can have for multiple derivatives of a function. Of course, f prime prime means two derivatives. Triple prime is three derivatives. But at some point, you want to stop writing primes after primes. So you also have this kind of notation where the number is between parentheses. This just means four derivatives of f, 5, and so on. Now, if you want to use the ddx notation, you can use it this way. It's kind of weird if you look at it at first time. The number of times that you're differentiating goes on the d at the top, but on the x at the bottom. I mean, the reason for that is if you think about ddx is the operator that means derivative. So if you want to take derivative of the derivative of a function, f, so you see on the top you have two d's. It's almost like they're being multiplied together. So you have d squared. And the bottom technically should have been dx parentheses squared. But anyway, this is just notation. You just have to remember it goes like this. Or according to the third item here, where the function goes in front of the symbol, the d square dx square of f of x. This means, again, two derivatives of f. So let's just do some examples here. Take a look at this. Compute two derivatives of the function x to the minus 3 times e to the x. So let's do that. Let's try to compute just one derivative first, and then whatever we get, we just differentiate again. Well, when you look at this, you realize that you need the product rule, or maybe the quotient rule if you want to write this x to the minus 3 as a denominator. But let's do the product rule here. If you remember how that goes, you need to differentiate each one of the two functions, but one at a time. And you add the two results like this. So x to the minus 3 derivative, that's the same thing as minus 3x to the minus 4. This is the power rule. And e to the x derivative is just e to the x. That's the one that you should all know by this point. So that probably for us, we probably want to at least factor the e to the x here, but you don't actually have to. I'm going to do that. We could also have factor maybe a power of x. But this is good enough for one derivative. Now let's take another. If we want to differentiate this again, double prime of the original function, well, by the product rule here, you have this function that we have up here. It is a product of two functions, one of them being e to the x, and the other being the sum of powers of x. So what I'm doing here is, again, applying the product rule to that expression, taking a derivative of e to the x first, right here, and then taking the derivative of the powers of x function right here. So this is all the derivative of the expression that we had for the first derivative. And what do we get from all this? Again, e to the x is just e to the x. Well, e to the x prime is just e to the x. And on the second term, what is the derivative of minus 3x to the minus 4? The minus 4 comes down in front. That's the power rule. You also need an x to the minus 5. And here, minus 3x to the minus 4. All right. Now, combining terms, we again have e to the x to factor from all of these guys. And you have minus 3x to the minus 4, x to the minus 3, plus 12x to the minus 5, and then minus 3x to the minus 4. So I'm going to at least combine the equal powers of x. You have 1x minus 3, you have minus 6x minus 4, and you have plus 12x minus 5. That's the second derivative of the function that was given. So there's nothing new about this. It's just taking a derivative and then doing that again. Let's see just the next one that they gave us. They said calculate the nth derivative of sine x for n equals 1, 2, 3, 4, and sorry, no 5, just 4. 1, 2, 3, or 4. So calculate the first and then second, the third, and fourth derivative of sine x. This should be very easy. One derivative. This is one that we need to remember. Derivative of sine is cosine. So two derivatives would now be taking this derivative, cosine, and then differentiating again. That's again one that we should remember, minus sine. Three derivatives. I'm going to take this second derivative, which is minus sine, and we need one more. What happens here? The minus 1 can come outside of the derivative, and then the derivative of sine is cosine. So the result here is minus cosine. Four derivatives. We're going to take this minus cosine and differentiate that. What do we get? If you bring the minus 1 outside and then differentiate cosine to get minus sine, you have two minuses making a plus, sine x. So the trig functions sine and cosine, they actually have this weird property that if you differentiate them enough times, you go back to the original function. We started with sine and we went through cosine, minus cosine, and then sine again. That's really not that usual. Most functions will not show this behavior, but it's true for these two. And by the way, this reminds me of one thing. If you're having trouble remembering the derivatives of sine and cosine, there's a little trick that you can use. Imagine the unit circle. We're going to write a few symbols here. You can think of it probably this way. The x-axis is where you look for the values of cosine when you're looking at the unit circle. And we can write here the places where cosine is positive and the places where it's negative. Similarly, when you look at the y-axis, up here sine is positive, down here sine is negative. Now, after you draw this, you just have to remember that the derivative is the operation of going clockwise. So ddx, for example, derivative of minus cosine is sine. So this allows you to remember the derivatives of sine and cosine, and technically also minus sine and minus cosine. All right, but enough of this. Enough of higher order derivatives. There really isn't much to talk about that. We'll return to this topic at the end, but we actually want to talk about the chain rule now. So here's the deal. Now we know how to find derivatives of functions constructed as combinations of other functions, but using the basic operations here, plus, minus, times, and quotients, division. But we actually still don't know how to find derivatives of composite functions, functions inside of functions. And here are just a few examples. Look at, for example, the function 2x plus 1. We're then applying another function to it, which is raising to the 5. We know how to differentiate each one of those pieces separately, but how do you take the derivative of the combined function? And similarly for the others. Now, I have some examples here that we should try to think graphically. The derivative of sine is cosine, but does that mean that the derivative of sine of 2x is cosine of 2x? It's actually no. This is something that we can probably think about graphically. So I had mentioned how the derivative of sine, the graph of sine looks like this. And that derivative is equal to cosine. Sine x, the derivative is cosine x. Now, sine of 2x, this is sine x. Let me draw sine of 2x in red. What happens when you multiply the argument of a function by the number 2? What happens to the graph? It actually gets squished by a factor of 2. So actually sine of 2x looks more like this. I guess I should have stopped here. This is approximately the same place that I stopped the first graph. You see that it's squished by a factor of 2. If you're looking now at any location on this graph, you realize that by squishing the slope of a tangent line, for example, let's look here, yeah, like in here, the corresponding place would have been here in the other one. The slope is also getting multiplied by a factor, in fact, by a factor of 2. It turns out that the derivative of sine of 2x is equal to 2 times cosine of 2x, not just cosine of 2x. So what's happening inside here is also affecting somehow this formula. And we're gonna see how. I just wanted to point out a few examples here. The next one also has an answer of no. Let's read it. The derivative of e to the x is e to the x. But does that mean that the derivative of e to the minus x is also e to the minus x? The answer is no. So once again, here is the graph of both e to the x and its derivative. Now, if you think about e to the minus x, that's the one that reflects around the y-axis. This is e to the minus x. Thinking about the derivative at any location here, we see that it's negative. This red graph is going down. The slope of the tangent line is always negative. So it would be impossible for the derivative of e to the minus x to be also e to the minus x. That's a positive number. E to the anything is always positive. What actually happens is that it's negative that. The derivative is this negative graph down here. So once again, it's the minus sign that was inside here, the minus x, is affecting the value of the derivative. Okay, so we need to understand better what happens when you combine two functions, like in here, the minus x function with the exponential function. That's what the chain rule is going to be about. So chain rule. The formula is right here. Let's read this. If g is differentiable at a point A, and then f is differentiable at the point g of A, because we're going to want to apply f to the number g of A, then this composite function f on g on whatever variable is also going to be differentiable at A. And the derivative, that expression, is going to be given according to this formula. It's a multiplication of the derivatives of f and g. This dot here means multiplication. And here you see g prime and f prime. But also important is the location where you're supposed to take those derivatives. G prime is calculated at A, but f prime is calculated at g of A. So you need to remember this. It is f prime times g prime, but it's important to say also where. And I guess this is what I'm saying, these remarks here. Let's actually read the second remark first. Each derivative must be calculated at the corresponding point, the point A for g and the point g of A for f. And the first remark is more like trying to get an intuitive understanding of this formula. Why are we multiplying this? It's a fact that rates of change, which is the meaning of the derivative, they compound by multiplication when the two processes are applied in succession. That's exactly what you mean by applying a function, like in this g first and then f. If you're gonna say multiply, if you're gonna affect the rate of change of g in some way, let's say multiply it by 2, and then also the one for f, let's say multiply that by 3, the combined composite function here will have a rate of change multiplied by 6, 2 times 3. That's the reasoning behind this formula with a multiplication. But the last thing here, how to apply this formula? Here is the formula again. I'm just applying it at any x instead of A. We're actually rarely going to use this form of it. We're gonna write a different form that's easier to use, easier to remember. But I want to walk you through this process here. Here's how you think about this formula when you're taking a derivative with the chain rule. You're going to recognize the two functions. One of them is called the outer function. The other is the inner function. It's very easy to see them in an expression like this, f of g of x. G is the inner function, f is outer. You want to give a name for the functions. For example, u for the inner function and y for the outer function. Notice that I'm writing y is equal to f of u. Why? Because y is actually this composite, but I was calling g of x my u. So instead of f of g of x, you can write f of u. That's your function y. Now, the derivative g prime of x, we have a notation for that that uses fractional notation like this, du dx. I hope you agree with this. U is the name that we just gave to the function g. So you can say du dx means derivative of g with respect to x. And the thing that we actually want, sorry, not the thing that we actually want. This term right here that appears on the formula, f prime of g of x, this you can think of as dy du. In other words, it is the derivative of the y function, the out function, but with respect to the g of x number, which is the function that we're calling u. So those guys are right here, the two terms that appear in the formula. The g prime of x and the f prime of g of x. And finally, the one that we actually want, this is what you can call dy dx. It's the derivative of the y function, the one that we are interested in, the composite, with respect to the variable that we want, the x variable. And the formula now looks like this. Dy dx equals dy du, du dx. It's very easy to remember because it's almost like you can cancel the du's in a fraction multiplication. But you have to remember these are just symbols. They're not numbers, right? That's the one that we want to usually apply these formulas to. I mean, we want to apply this formula to problems involving composite functions. So let's stop talking about this and actually show you some examples. Calculate the derivative of sine of ln of x and state the domain where the formula is valid. So you call y the function that you want to differentiate. And when you look at it, you realize it's a function of a function. There is an inner function that you should call u. And there is the outer function, which is sine of, well, ln of x is u. Those are the two functions involved. You want to try to find their derivatives with respect to each one of their variables. Du dx is 1 over x, the derivative of ln x. This is valid for x positive. And dy du, I'm looking at the second formula now. Dy du, derivative of sine is cosine, cosine of u. This one is valid for any u. Like u belongs to negative infinity, infinity. Now the formula for the thing that we want, which is dy dx, just always remember this. Again, you introduce the du terms, you introduce two fractions. So you're going to be multiplying these two guys, dy du and du dx. This is what you get. But your last step, which is always the easiest one, it was originally a function of x. We're looking to write this also as a function of x. You still have a u in this formula. So you just want to replace the u with what it means in terms of x. So you have it right here. U means ln x. So we can write this as cosine of ln x times 1 over x. This is the derivative of sine of ln x. I'm going to be spending time doing it always in this way in today's lecture. Over time, you're going to be able to do this straight. It's not that easy really to see. We have the what you maybe could think the derivative should be, cosine of ln x is right here. But you also need to multiply that by the derivative of the inner function. So you're going to be able to think of it very quickly. But I'm still going to be doing things slowly today. And by the way, what is the domain here? The only restriction that we found, the u could be anything, but the x had to be positive. So we have to say x positive here. So let's move on to the other one. Calculate d dt of the function square root of t to the fourth plus 3t squared plus 5, and state the domain. Okay, so let's call y the function. This time we actually want to find dy dt. The variable was given to us as t. The independent variable. The thing that we want to find is dy dt. Well, we will look at y and you realize it is a function of a function. There is what you can call an inner function, u equals t to the fourth plus 3t squared plus 5. And there is the outer function, the y is the square root of u. So we need to find the derivatives of these two guys separately, du dt. That's easy with the power rule. I'm applying this here very quickly. What is the derivative of, okay, so this one that I just wrote down for t cubed is the one for t to the fourth. Now, what is the derivative of 3t squared? The 3 is just a constant, and the derivative of t squared is 2t. Finally, the derivative of plus 5 is 0. It's just a constant. Okay, so this gives you 4t cubed plus 6t. And the domain here, any t, any real number t. Finally, the y du. Well, y was the square root of u, which you can write as u to the 1/2. You're trying to find the derivative of that. That's 1/2 times u to the minus 1/2, which becomes 1/2 root u. You may have memorized this by this point, the derivative of its square root. This one here is only valid for positive u, because there's a square root, because the u is in the denominator. Okay, now you just put those two things together. The chain rule is this formula. The thing that you want, dy dt, in terms of the two things that you could find, it's just the product of the two. dy du, du dt. So now dy du is 1/2 root u. dy du dt is 4t cubed plus 6t. And you want to put this all in terms of the original variable, the t variable. So you wanna rename the u with what it actually means, which is right here at the top. That's what I'm gonna do here. So in this multiplication, I'm gonna write the 4t cubed plus 6t in the numerator. And downstairs, instead of root u, I'm writing I'm writing t to the fourth plus 3t squared plus 5 it was. Yes. And then what is the domain for this? The two restrictions that we had found, t could be anything, and then u only has to be positive. But if you look back at the u in terms of t, this number is always positive. You only have even powers, and then you also have this plus 5. This number will always be at least 5, right? So you really don't have any restrictions on the t variable. Basically, usually you don't have to do this usually, but if you're looking for the domain, you have to translate this new variable that you introduced, the u variable, in terms of the original variable t. The places where u is positive in terms of t is every place. Every t makes u positive. So this does not impose any conditions for you. That's the derivative. This is two examples where I'm changing the roles of the inner and outer function. They should be very quick. At this time, we're not even asking for the domain, just the formula. In the first one, we want ddx of the function sine of x to the 7/2. The inner function here is x to the 7/2. The outer function is sine of u. So you find the derivatives, du dx, power rule, 7/2, x to the 7/2 minus 1, which is 5/2. and dy du, derivative of sine of u with respect to u, cosine of u. Multiply those two together to get dy dx. So right here, dy du is cosine u, du dx, 7/2 x to the 5/2. But don't leave your answer like this. Replace the u with what it means. Instead of u, I'm going to write x to the 7/2. So this is your answer here. I moved the 7/2 to the front, the number. Now in the item B, you notice that, well, we have some, I guess, some work to do here. In item B, the function, it was written in this format, sine to the 7/2 of x. What this actually means, when you raise a trig function, the whole function to a power, you can write that power also on top of just the name of the function like this. We usually see this with sine square, right? As long as it's not the number -1, because sine to the -1 is kind of ambiguous, but we don't have to worry about this. This is the function that we actually have. In this form, I think it's easy to see which one is the inner and which one is the outer function. The innermost function right here is the sine function, the one in parentheses. And the original function is that raised to 7/2. So now we find the derivatives here, du dx. Derivative of sine is cosine. And dy du, I mean, we kind of already found these guys above. They were just applied to different variables. But we multiply those two. dy dx is dy du times du dx. That's chain rule. Well, dy du is 7/2 u to the 5/2. And then du dx cosine x, where u this time is actually equal to sine x. So we have sine x to the 5/2 cosine x, which we can also write, again, using this special notation for powers of trig. You can write this 5/2 power on top of the name sine. It means the same thing. That's your derivative here. Moving on. This is one of those questions that secretly is asking you for a equation, for a derivative. But instead of just asking for a derivative, they're being more precise with find the equation of the tangent line to the graph. So we have a function and a point on the graph of that function. If you plug in x equals 1/2 in here, you have cosine of minus pi to pi over 4, which is √2/2. So this is a point on the graph of this function. And we want to find the equation of the tangent line. I should remind you, this is how you find the equation of a tangent line on a point where the x coordinate of this point is this a, the y coordinate is f of a. So the y value of the point is f of a, the x value is a, and the slope is the derivative. We're gonna, this is the answer that we need. So we need to find f prime. What is a again? A is the x coordinate of the point given. We need f prime of 1/2. That's why you need a derivative before you can talk about the tangent line. So let's find f prime of 1/2. Well, before you find f prime on a number like this, you want to find f prime of any x. You want to find a formula for the derivative, because then you can apply it to that number 1/2. So our first step in this problem is going to be find the derivative of this function. So f of x, let's call it y. It was given as cosine of minus pi times x squared. That's the function that we have in the problem. This is one function that's going to require the chain rule. So let's call u the inner function minus pi x squared, and y the outer function cosine u. Du dx is the derivative of minus pi times x squared is minus pi times the derivative of x squared, which is 2x. So instead of writing minus pi 2x, I'm writing minus 2 pi x. And dy du is derivative of cosine is actually minus sine. I hope you remember that. So the derivative of the dy dx, which is the same thing as f prime of x, now that we have a name for this function, which is f, you're going to multiply the two numbers together, minus 2 pi x minus sine x. I have a typo here. I hope you caught it. It's not x, it's u. You see that I just noticed the way that I was going to write it here, I have x in both variables. That's not usually the case, right? Well, it's because I have a typo up here. Let me do this in another color. Dy du is minus sine u. If y is equal to cosine u, the u is the derivative that you're taking, the variable that you're taking a derivative with respect to. So this is actually sine u here. And now we're good. You have minus 2 pi x times minus sine of, what is u? U is minus pi x squared. Okay, I guess we can at least cancel the minus signs. This is 2 pi x sine of minus pi x squared. That's f prime of x. How do we find f prime of 1/2 now? Remember, this is the number that we actually needed in this question. Well, we have the formula for f prime of any x that you like. So you just go ahead and replace that with 1/2. 1/2 squared is 1/4. And this is an angle whose sine we can find. So first of all, 2 pi times 1/2 is just pi. And now this angle is minus pi over 4. Thinking about the unit circle, minus pi over 4 is on the fourth quadrant. This is an angle with a negative value for sine. It's minus root 2 over 2. It's the angle of minus 45 degrees if you prefer to think about degrees. So this derivative involves root 2 over 2 and also pi, and it's negative. Now you're good to go. The formula that you wanted, remember, here comes f of a, which was root 2 over 2. Here is the slope that we just found, the value of the derivative, and then x minus a is 1/2. You can leave it this way, in this way. Let me just double check that these were the correct values. Yes, you see here a and f of a, both positive, 1/2 and root 2 over 2. Those are right here. All right, moving on. Consider f of x equals 3x minus 1 squared. Instead of asking you to differentiate this directly, I'm going to ask you to do it both times, 2 times. The first one is expand f of x by the binomial theorem and then compute the derivative directly. So they're asking us to first expand fully what this square is. If you know the binomial theorem, square the first term minus 2 times first times second plus square of the second. Square of minus 1 is plus 1. You can also get this by just distributing. This is the same thing as 3x minus 1 times itself, right? That's how I'm doing this. So you see that if you expand out your f, it actually becomes a polynomial, and we know how to differentiate those. This is actually 18x minus 6. I hope you know this. What I'm doing is the 9 is unaffected by the derivative, and the derivative of x squared produces 2x. So that's how I got 18x. And this minus 6 comes from minus 6x. Whereas the plus 1 is irrelevant for the derivative. So this is f prime. Now B is saying compute f prime by the chain rule. Instead of doing this, they want us to look at the original expression, 3x minus 1 squared, and apply chain rule to this. You'll notice that there is an inner function, 3x minus 1, and an outer function, the square of that inner function. So du dx is 3. dy du is 2 times u, derivative of u squared. Now dy dx, the derivative of f of x, is 1 times the other, dy du, du dx. So you have 2u times 3, or just 6u. This is what it is in terms of u, but you actually want this in terms of x. So just use the formula for u. Replace u with 3x minus 1, and you get 18x minus 6. It's exactly what we got in item A, so that's good. I'm probably going to skip this one. It's really not that interesting. You should try it anyway. I'm giving you a function that's secretly the number 1, sine square of x plus cosine square of x. That's always 1. So item A is saying how much do you expect the derivative should be? The answer is 0, okay, because 1 prime is 0. But B is saying compute f prime using the definition. So take the derivative of this expression, sine square plus cosine square. See that you get 0, which is the answer that you expect. But I'm going to skip this calculation. This one will be more interesting for us. So consider f of x equals e to the 5x. Again, we're going to find f prime in 2 different ways. First one is saying compute f prime considering e to the u as the outer function and u equals 5x as the inner function. So it's like this. The 5x in the exponent is the thing that we're going to be calling u. And e to the u is the function. This is what we call y. So we're going to be considering these two guys. Du dx is 5. dy du, derivative of e to the u with respect to u is e to the u. Multiplying the two will give us dy dx, or f prime in this case. 5 e to the u is equal to 5 e to the 5x, because u is equal to 5x. That's the answer. The point of this question now is to show you that sometimes you have more than one choice for what's the inner and the outer function. In this case, they're saying compute f prime again by rethinking the expression as e to the x to the 5. This is also the same function. If you wanted to multiply this 5 and the x here, you get the original e to the 5x. But when you look at the function this way, you realize that you have the inner right here, e to the x. And that thing is being raised to 5. You can call that the outer function, raising to 5. This also gives you the same function. So you should get the same answer. Let's see that we do. Du dx now is e to the x. dy du, you need the power rule for this. Derivative of u to the 5th is 5u to the 4th. Now put those two together to find dy dx. You're going to get e to the x times 5u to the 4th. 5 e to the x. Instead of u, I'm going to write e to the x to the 4th. Okay, how do we simplify this expression? You realize here, just think of e to the x as one number, one variable. It's raised to 1, and then times it's raised to 4. So that's like, think of it this way, raised to 1 times raised to 4. That's the same thing as raising to 5. And that's also, by the way, 5e to the 5x. The same answer from before. So yeah, sometimes you have more than one choice for your inner and outer function. As long as you have a valid choice, you're gonna get the valid answer. And now I wanted to mention, by the way, sometimes you can have more than 2 functions being composed together. Here's the chain rule for a composite of 3 functions, f of g of h. How does that work? In terms of the original formula that you sometimes need, sometimes it's better to think of it this way. It is, again, multiplication of the derivatives, f prime times g prime times h prime. But they are derivatives calculated at the corresponding numbers, g of h of x, and just x. If you call those guys functions, like innermost and then intermediary and then outermost function, basically you can think of the formula this way: dy dx. We're gonna be thinking about 2 intermediary functions, u and v. So dy dx is dy dv, dv du, du dx. Just like if you could cancel out the du's and dv's. So this is the one that we usually want to think about when looking at formulas, like this one. Compute d dx of this particular fraction right here. How do we do this? There's a lot going on in here. Why is this function 1 over secant of x e to the x, the whole thing to the cube? When you look at this, try to find the innermost function, the one that's the most inside parentheses and the one that you can differentiate without a chain rule. It should be x e to the x in this case. That's the one that I'm going to call u. We know how to find du dx. The next function that we have, you have secant of that expression. This should be our v function. Secant of that expression, secant of u. Finally, you have this outermost function that you can consider, 1 over that thing to the cube. Y is equal to 1 over v cubed. You can write it this way. This is a function that we know how to differentiate. You could also have considered the cube to be yet another intermediary function. And then the final function is just 1 over that. So you'd have 4 steps. That's up to you. But this is a valid choice right here. Now we just need to find the derivatives of each one of these guys with respect to their variables, du dx. Well, this one, du dx, I'm looking at the first formula. This requires the product rule, so I'm gonna be writing this carefully, I guess. That's how the product rule works. X prime is 1, e to the x prime is e to the x. And I'm probably gonna factor the e to the x here. To write this as 1 plus x e to the x. That's du dx. dv du. The derivative of secant is one of those that I told you should probably memorize. It is secant times tangent. If you don't know, you can always compute this by rewriting it. Secant is the same thing as 1 over cosine. This one you definitely know how to differentiate if you use the quotient rule. And you're going to find secant times tangent. Finally, the y dv. If y is v 1 over v cubed, that's the same thing as v to the minus 3. Taking a prime of this will give you minus 3 v to the minus 4. Now we just put all of those together. dy dx is dy dv, dv du dx. So I'm going to multiply the 3 results. And finally, convert everything only to functions of x. Look at right here, up here. U is x e to the x. So I'm going to at least replace those guys right here. Instead of u, I'm writing x e to the x. But the v is also something that we know how to write in terms of x. V is secant of u, and u is x e to the x. So v is secant of x e to the x. That's your final result. And you see that you can simplify this a little. At least the product of the two secants here. You have a secant to the -4, and then you have it to the 1. So you can write it as to the -3. And you can even put that, we probably should not do that because it's a negative number. So I'm just going to do this. Raised to -3. I'm combining these two guys. Because this is easy enough, you should do it. Might be useful, whatever you're doing to this function. All right, so that was a chain rule applied to 3 functions. I have one more example of that in here. Maybe I don't finish it. I don't want to extend this video too much. But this is a multiple derivative. It's 2 derivatives with respect to the t variable. And the function is, again, three pieces that's easy to visualize. ln, sine, and then square. Y is ln of sine of t square. And we want to find 2 derivatives of that. I'm going to find at least one here. So the innermost function is the t square function. Next, you are applying sine to that. And finally, to obtain your final function, you are applying ln to the previous function. Those are the 3 that we should be considering. They have very easy derivatives. du dt is 2t. dv du is cosine u. dy dv is 1 over v, the derivative of ln. Multiplying the 3 of them together will give us dy dt. Only one derivative of the original function. So I'm going to write this as 2t times cosine of u. Well, u is t squared. And the whole thing is divided by v. I'm writing this 1 over v as a denominator with a v in it. But the v is sine u, which is the same as sine of t squared. So I guess if you want to color code this so you understand what the variables actually are. But this is one derivative. This is dy dt. How do you actually find 2 derivatives now? Like this. Which means, by the way, derivative of the derivative. Well, you basically have to differentiate this function again. The result that you just found. Take a prime of that now. Good luck with this. I'm not going to do this. It will take some time. But when you look at this, you don't see anything that requires this special chain rule that we were just talking about with 3 functions. There is nothing like that. This is more something that will require the quotient rule because it is a fraction. There is a product rule up here. You have 2t times another function. And this other function requires the chain rule, cosine of t squared. Also, the denominator requires a chain rule, sine of t squared. So you have to be careful when you do this. This one is a big one. If you want to know the answer, I mean, I don't have it, but you can ask me in office hours probably. All right, so with this, I'm going to finish the video.